All right, so if we want to sketch these they're going to be called energy profiles. Sometimes maybe an energy diagram. If a reaction is endothermic, we'll call this reaction A becomes B, just to make it simple. All right, we're going to have potential energy. Maybe it just says energy, but maybe it says potential energy on this axis. And then on our x-axis, it's just going to be as the reaction proceeds. Maybe not related directly to a number of seconds or anything. All right, so if a reaction is endothermic, then it must overall increase in its own potential energy as A becomes B. So we're going to still have a hump to go over, but we're going to be uphill overall. And then on this graph, whatever the difference is from start to the top of the hill, that is called the activation energy barrier. So I'm just going to call it EA. Energy of activation is represented there. I could extend this out a little bit more and talk about delta H again. The change along the y-axis from A up to B would be considered the delta H, and I know it's a positive number here because it's a positive change. It's uphill overall. Then we're going to do the same thing with this exothermic reaction over here. Potential energy, maybe just energy, is going to be on this axis. Sometimes they'll have numbers, but sometimes they're just going to be, again, conceptual, just to see that the change is positive or negative. Of reaction, let's just say it's A to B again. But if it's exothermic, then it would start off with more energy, and it ends with less potential energy because energy was released to the surroundings. It gave off heat overall. All right, so they're also going to have activation energy barriers. Not necessarily greater, not necessarily less. Depends on the reaction. And then it would also have a value for the delta H. It's just the difference from start to finish. In this case, it would be negative because it's downhill overall. So we want to be able to find these activation energy barriers for different reactions, and eventually we would compare them with each other. So if you looked at one reaction that had a really high activation energy barrier, that one's probably going to be slower than a reaction with just a really small activation energy barrier, as long as everything else is basically the same. So we'll use these. This is how these graphs, right now it's just about energy, it looks like, but it's related to the speed of the reaction, because reactions with high energy barriers are relatively slow. Reactions with really short energy barriers are relatively fast because they don't take as much energy to get started. So more particles are more likely to overcome that barrier. All right, so that's looking at those graphs. Let's move on to, here's one kind of, what does this all mean? I've got this one printed on your little sheet down below there. You can actually kind of see how that would relate to the specifics of an individual reaction. So this is showing us a pretty simple reaction. One reactant here by itself is going to turn into a product of itself. All it's doing, something, it can happen with a more complex reaction, but this one's just kind of simple, so you can put all the molecules on there. It's just flipping around its blue atom and its black atom there, so the nitrogen and the carbon. So it's becoming an isomer of itself for this reaction. But in the end, you can see it starts off as a reactant. This gets into kind of what we call the mechanism, the step-by-steps, what's happening at that individual molecule level. The nitrogen and the carbon are actually flipping around each other. At the very top of the activation energy barrier, you have what's called an activated complex, something that's very unstable. It's a very unstable molecule. You've never seen a molecule that would have a triple bond that's just sideways compared to the rest of the molecule. And then it continues to flip around. And this one ends up having less potential energy in the end, so it must have been exothermic. It must have released some energy there. So that's what that activation energy barrier is all about. How much potential energy does this really weird, uncomfortable molecular position take at the very top of that curve? All right, and it's unstable. When something is unstable like that, we say it has high potential energy. There's another word for that activated complex, which is sometimes called transition state, because the molecule is in transition. It's not its reactant, it's not its product yet, it's in transition. So sometimes you'll see that called transition state. So I might ask you to find a transition state on a graph like this, and just know that's the same thing as the activated complex in that picture. And another kind of synonym, it's almost the same word even, the activation energy is more of the number. The activation energy barrier is the graphical representation of that. So the activation energy might be 50 kilojoules, but the activation energy barrier would just be on the graph. It would be the hump on the graph. It's basically the same thing. One of them is just more specific to a number, and one of them is more of a picture on a graph. So those two words are basically synonyms for some things that are on your graph already, but just in case you see those on a question, that's what they mean. So I've got one more slide of some definitions to put down on these white spaces, and then on the back we're going to solve the problem that you see on the back. So if you can still fit this somewhere on the front, that would be ideal if you've got any more lines left on the front. So relating this stuff to the rate constant, activation energy, and temperature here. So we said a minute ago the rate constant itself is temperature dependent. So if you have a given reaction and you're going to compare it at two different temperatures, then as the temperature increases for that particular reaction, the rate constant itself would increase to speed up the rate. And that's going to be because, we'll see on a graph on the back, a greater percentage of the reactant molecules have enough kinetic energy to make those successful collisions and overcome the activation energy barrier, because those particles are moving faster and they're colliding more frequently. The other thing you'll sometimes compare is two different reactions to each other. All right, so if you're comparing two different reactions to each other, the one with the higher hump to go over is going to be relatively slower, so it must have a smaller rate constant, assuming everything else is pretty similar. That's what we'll be comparing, stuff like that on the back of your sheet. Yeah, Josh. That's a great question, because the answer is no, and it's important to think about why that is. He said that would increasing temperature change the activation energy barrier for a particular reaction? No, it does not, but it does allow more molecules to go over the activation energy barrier. We're going to find out, it's next week, but the only thing for a given reaction that will lower its activation energy barrier is adding a catalyst. Temperature, it's still the same molecules, they have the same bonds, so their potential energy changes are still going to be the same. So changing the temperature does not change the activation energy barrier itself. It just lets more reactant molecules overcome the activation energy barrier. It's a great question. All right, so, and it kind of is related. Once we see some of these graphs, some of that stuff will make a little more sense. The point of this slide, though, is there's two things I might ask you to compare. I might ask you to compare two different temperatures for the same reaction, or I might ask you to compare two different reactions to each other. And that's what the last bullet point would be about there. All right, so if you flip this over, I'm going to turn the lights on because I wanted to print all this stuff on the same page, but the font is really small on your sheet there. Just so you can actually read what I can see on the screen. I hope you can kind of make it out. We've got an energy profile here, and we're going to answer some questions about it. First it says, is the reaction endothermic or exothermic? Well, we're starting kind of in the middle of the graph. We're ending at the bottom of the graph. So what do you think? Is this one going to match the endo or exo? Exo, yeah. So if you start with more potential energy than you end with, that's going to be exothermic. I'm going to put a little note there also so we don't forget about our old friend delta H. That would be a negative value for a delta H. Actually, I even know what it is. It's negative 15, which is coming up on number 3, so just forget about that. Number 2 says, what is the value of the activation energy? All right, so it's from where we start to the top of the hump. What does it show on the graph is from the start to the top of the hump? 25, yeah. So activation energy, I'll call it EA, equals 25 kilojoules. Activation energies will always be positive numbers because they're always going over a hump, so they're always an uphill battle. That's a good question. Kilojoules per mole is a better unit for it. Sometimes it might just be in kilojoules, though. That number, again, kind of like on the bell ringer we did, it's related to 1 mole of anything that's a 1 coefficient in the reaction. All right, so what's the value for the delta H for this reaction? What would we say? Yeah, negative 15. Kilojoules is fine, or kilojoules per mole there is even better. All right, so something we haven't looked at quite yet is a reverse reaction. So if we were to take a reaction that was just, let's say it was A becomes B, and we wanted to flip it around, and we wanted to know B becomes A. So we're just going to ride the roller coaster backwards here. All right, so if we started at B, we'd have to go up 15, then we have to go up 25 more to get to overcome the hump. So if we rode this reaction backwards, this is our reverse activation energy barrier. So what would the total be if you went up 15 and then you still had to go up 25 more? Yeah, that would be 40. So for the backwards reaction, the activation energy barrier is 40 kilojoules per mole. Oh, sorry, that's I keep moving stuff in the wrong place. That's the answer to 5, isn't it? Just let me move it. Not all of it. Oh, there we go. Answer to 5 there. 4 was endo or exothermic. So if you go from A to B, it's exothermic. So therefore, if you went backwards from B to A, would that be exo or endo? Endo. We did this a while back when you flipped a reaction around. Remember, it flipped the sign of the delta H. So now we're going to be endothermic for this way. And that's related to number 6 also. So 6 says, what's the value for the delta H for the reverse reaction? Well, if you go from B up to A, how far do you have to go up? 15 kilojoules. Again, you're flipping a reaction around. So now we're positive 15 kilojoules. So I'll be asking you some questions on your assignment about flipping a reaction around. It just means you read the graph backwards. You still have to go from wherever you're starting, whether it's A or B, up to the top of the hill. So just think about it like riding a roller coaster backwards. All right, any questions on working through those problems? All right, and so let's just look at the other 2 things on here. So I've got another set of questions comparing 3 different reactions to each other. All right, so When you're looking at one energy profile at a time, you're focusing on that one reaction. Now we're looking at 3 different reactions. They all have their own activation energy barriers, their own delta H's. So we can compare them to each other to figure out which one would be the fastest or slowest. So it says here, consider a series of reactions having the following energy profiles. All right, I've got first one, second one, and third one. And then it says, rank the reactions from slowest to fastest. Then it says this little part, assuming they have nearly the same frequency factors. That is related to what I mentioned at the beginning of the class about the complexity of molecules. If one of these had really complex molecules and one had simple molecules, we wouldn't want to compare them to each other. It wouldn't be fair. But we're assuming they're about the same complexity, so one's not going to be extra slow just because it's made of these big complex molecules, and the other one has an advantage because it's made of simple, really small molecules. That's what that means. So it means we're allowed to compare them. All right, so let's look at the activation energy barriers to do that, because remember, the greater the activation energy barrier, the slower the reaction overall. So just a little note about how we're going to approach this.
Students that are going for local government day, please meet in the front lobby. Thank you.
You heading out? All right. Greater activation energy barrier means slower reaction. Slower rate. All right, so which one, we're going to rank these from slowest to fastest. So which one would be the slowest of all based on that idea? Remember, the greater, 2. So again, it's kind of a maybe inverse kind of relationship you might think about there. So we're going to compare those numbers to each other. Those are our activation energy barriers. And you're right, the middle one is going to be the slowest. So I'll call that one number 2. It's the slowest one. I'll use less than. So then which one's going to be in the middle of the ranking here for medium speed? Yeah, number 3 is going to be in the middle. It's got 20 kilojoules per mole for its activation energy barrier. It doesn't matter that one's endothermic and one's exothermic. All right, and then which one will be the fastest of all? Have to be the last one, right? I mean, the only one left, the first reaction. Reaction 1 is the fastest because it has the smallest activation energy barrier, which means at a given temperature, the most fraction of reactant molecules have enough kinetic energy to overcome that energy barrier. All right, so that's how we can just compare the speeds of different reactions based on their activation energy barriers. Last thing to look at gets back into how temperature is related to this stuff. So again, the color picture looks a little bit better than the black and white one that you've got on there. But when you have a sample of molecules, this graph that we're looking at right here is not like the graphs we've been looking at so far today. It still has a curve to it, so you might think at first, oh, it's just one more of those. This is a very different one because look at the x and the y-axis. What's your x-axis on this graph? Kinetic energy, right? So this time energy is on the x-axis. This is not one of those roller coaster over the hump kind of things. Here we're looking at basically like almost a statistical bell curve of particles. So if you remember, like when we were talking about gases and I put the simulation up on the screen and like I pumped some gas into there and the particles were moving, all right? At any given temperature, some of those particles were moving faster than others, but there was an average speed, all right? And that's related to the top of this. Just like if this were a bell curve for your grades or something in here, maybe the blue line would be at a cold temperature. There's your average speed of the molecules, moving about that fast. Some of them are moving slower, some of them are moving faster. All right, so the blue would be at a relatively cold temperature. As you heat up a sample, all right, the bell curve is going to shift to the right. It also gets a little bit shorter because it gets stretched out, but it shifts over to the right because the average particle has more kinetic energy, even though a few of them are always moving faster and a few are moving slower. All right, so it might be like there's grades in one class, and then in another class, maybe they got to use their notes or something, and so they're going to get a higher you're going to get a higher average, even though some people are still doing better than others. It's the same thing with the speeds of the molecules at two different temperatures. Well, also, remember this is the energy is our x-axis, so there's some kind of minimum amount of kinetic energy that the particles need to get over the hump. So if we relate this to the previous graph, maybe the first one we were looking at, it had an activation energy barrier of 15. So maybe that's a 15 right there on the graph. Sorry, I hit the wrong button. All right, so maybe on my graph, maybe that was 15 if I'm looking at the first of the three graphs in that last problem we were looking at. So at a higher temperature, a greater fraction of molecules have the 15 kilojoules that they need to overcome the activation energy barrier. All right, so that would be different. That minimum energy would be different for every single reaction you were looking at. But no matter what, if you increase the temperature, you're going to shift that line to the right. The red line is represented here. If you increase the temperature even more, it would continue getting shifted to the right. So therefore, a greater fraction of particles can overcome the activation energy barrier. So that's why when you're comparing the same reaction to itself at different temperatures, the activation energy barrier doesn't move, but the curve actually shifts, so a greater fraction can overcome the activation energy barrier. Does that make sense when you're comparing the same reaction to itself? All right, so that actually basically finishes up our notes for us there. You've got, I guess there's one more sentence on here just to compare here. So therefore, that's why as temperature increases, the rate increases and that rate constant increases also. All right, so you've got an assignment that kind of goes over this, and you're going to read a lot of these graphs on Canvas. It's called Kinetics 04, so you can go ahead and get started.